Alright, so today we are talking about water. Water is known as the common solvent, is what they say in the book. That's because we use it to dissolve many things, and that's got to deal with its molecular structure. It's no surprise there. So water, I'm just going to draw a water molecule for you guys. Water is made, obviously, out of one oxygen and our two hydrogens. I'm sure you guys remember seeing these molecules all over the place. And so it is a molecule, it's a covalent compound, it's between two nonmetals, remember that? And so because it's a covalent compound, that gives it the ability to have what's called polarity. Hopefully you guys heard about that. I did talk about it a little bit in regular chem, so for anybody who had me, you guys probably heard of it. And what happens is, the more electronegative you are, the more you take those electrons or attract those electrons in the molecule and create what's called an uneven bond, because remember, they're being shared in this case. And I always explain it like, for instance, let's say I have a marker shared between me and the teacher next to me, Ms. Severino, but the marker mainly stays in my class. I'm going to be the more electronegative atom. I'm going to be the one that hangs onto the electrons more. And so that's the same case scenario with here. And so what happens is, this little symbol means it's a partial positive. And so we have partial negative. So oxygen's more electronegative, so they're going to have a partial negative charge on the oxygen, where on the hydrogens, we're going to have partial positives. Okay? A lot of times you'll just see me write them as little positives and little negatives. Understand that that's just because I'm trying to go a little bit quick sometimes in class, and but this is the symbol to represent that. The ones that I just drew kind of looks like a little music note. All right, so now I want to talk about things like salts. Okay, let's talk about specifically sodium chloride and its interaction with water. I'm not going to do red just because of the fact I don't want to confuse this. Okay, and so if we got sodium chloride, I'm going to make these molecules kind of larger. There we go. Okay, and if we got sodium chloride is an ionic bond. We have a metal in there. Sodium is a metal. It's to the left of the staircase. And so these guys aren't sharing electrons. They're actually, basically sodium gave up its electrons. And so I'm going to right now label these guys. Sodium gave up its electrons and got a positive charge. And it gave its electrons to chlorine, which then made it negative. Okay. Now, this is kind of significant because when we talk about salts and how they actually, what's called hydration, when they interact with water, they hydrate. And what's going to happen is your sodium, sorry about that. Your sodium's going to separate from your chlorine. And remember, these guys are still hanging on to the charges that they previously had. So let's see, we got sodium with a little positive, and we got chlorine with a little negative. But now what I want you to see is what water does, and you'll have to get used to drawing molecules here. When water interacts with these guys, the oxygens, or the partial negative charge, is going to be surrounding that positive cation of the sodium. And on the reverse of that, so here we got all the negatives, and I'm going to kind of draw this with a little, hopefully little negatives. Okay, let's undo that. Let's make that a little bit tinier. All right, so the partial negatives on all the oxygens, okay, are basically being pulled towards that positive charge. So this negative on these oxygens, the partial negative charge, is being pulled towards it. Okay? And when they're attracting, when those negative charges are attracting that positive cation, it separates it from its previous bond. Okay, and now on the reverse of that, when we go ahead and look at the negative anion, what's going to happen is, we're going to go ahead and label these guys. The positive or the partial positive hydrogens are going to be attracted to that negative chlorine. And so it pulls away from each other. The water is basically acting as a force to separate the two. So we got a little positive, 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 and one more little positive. And so basically it separates the two. And this process is kind of known as hydration, is what they talk about in the book. Okay, and it's just basically when water is able to separate the two molecules. It's another way of also saying to dissolve anything. So that is how water is able to dissolve. Oh, that's not what I want.
Hey, you have some kind of package for me?
Separate. All right, and next one, we're going to be talking about 4.2, which is the nature of aqueous solutions, strong and weak electrolytes. So first things first, I want to just remind you on basic vocabulary. So I'm going to go ahead and remember that the solute goes into the solvent, and together this is called what's called a solution. Okay, so now we also have to talk about a little bit more vocabulary. We got the word electrolyte. And you guys have probably heard of it all the time in your energy drinks. Being a runner, I always have to really watch my electrolytes because I keep on sweating them out. And they play a huge role in our sodium, potassium, all of the pumps in our body. I want to say it's sodium, potassium, but now I feel like that's the wrong pump, but those pumps along the lipid bilayer that you learned about in biology. They're useful to note because they're going to conduct electricity. And also they dissolve or separate in water. They're going to be ionizers. So there's differences. We got strong electrolytes, weak electrolytes, and non-electrolytes. Water itself, as much as you guys would like to argue with me that it does conduct electricity, pure water does not conduct electricity. Okay? It's the electrolytes that are in the water. Now, I'm not saying that if there was just water and that, you had a case scenario where you wanted to cross a lake and it looked like it was, transmitting electricity, to do that, because, to tell you the truth, ions are everywhere. They're surrounding us all over the place. But pure water does not conduct electricity. It's the electrolytes within the water that do that. Hence the reason why we need to talk about them and their different types. All right, so let's go ahead and first talk about strong electrolytes. All right, and so strong electrolytes. We got a few different versions, okay? These are going to be anything that separates within water, okay? Or completely ionized when they're dissolved in water. So things that dissolve will be our soluble salts, such as sodium chloride. Do you guys remember strong acids? Any strong acid completely dissociates, Okay, and so because they're going to be completely dissociated, they're going to be our stronger electrolytes. And then also, strong acids separate, but also do strong bases. Once again, they completely dissociate, so as long as you can identify the three, that will help you a lot in this upcoming chapter. So soluble salts, we'll kind of talk about this in class. Soluble salts work through the solubility rules, which you will have to memorize a few of them, not all of them, but the solubility salts will kind of abide by those rules for us in class. Strong acids, there's 7 I'm going to be making you memorize eventually. Those are going to be all strong electrolytes. And for strong bases, our strong bases are just our group 1 cations with our hydroxide anions. So those guys are all strong electrolytes, which means they completely dissolve or completely ionize. Okay, these guys are guys who love to separate. Alright, so let's talk about our weak electrolytes. Weak electrolytes are different than strong electrolytes. They don't completely ionize. These guys will be partially ionizing, okay? So these guys partially ionize. And that's kind of huge. How do we know what they are? They're going to be weak acids, weak bases. Because they're not fully separating, they're not going to transfer electricity as well, and they're going to be a weak electrolyte. So anything that's not a strong acid will be considered a weak acid. Anything that's not considered a strong base will be considered a weak base. We'll talk about that a little bit more tomorrow, but just so you guys know, that's kind of a huge part of this. Okay, so I was trying to write this, and we'll go ahead and finish it. Oop, let me turn back to my pen. Okay, so non-electrolyte. Okay, so non-electrolytes are substances that don't produce ions. And what substances don't produce ions? I want you guys to think about it for a second. It's got a hint. It goes with the word molecule. Okay. We actually only use molecule with covalent compounds. Okay, remember covalent is between 2 nonmetals, and so our non-electrolytes are going to be mainly our covalent compounds. And just to refresh you guys, I know you guys probably get tired of the refreshers, but you know, I gotta drill this in your head. Our covalent compounds are going to be between 2 nonmetals. They don't form that cation-anion relationship that we're looking for. All right, now our last but not least problem, not so much problem, but more topic. I just want you guys to go over the dilution equation. And the dilution equation is M1 V1 equals M2 V2. And all of this is for your initial solution. And all of this is going to be for your solution. You are going to, or you want. Okay, we'll go over some examples of this. I do believe that it's covered in your homework, but I want you guys to try some of these on your own, just because we reviewed a lot of this in regular chemistry. I want you to take a stab at it. We'll talk about it more tomorrow.